Hey, Katie.
Hey, Ben.
How has the weather been?
It is warm here in Chicago. They have humidity in the Midwest,
Oh.
not like California.
Yeah, it's really nice right now in California.
Yeah, but you guys are
It's June
cheating here in
15th.
California. But we have a lot of reasons to think that maybe the weather in the very long term will not be particularly as nice right now. We say this on the basis of climate models that people run. I wanted to talk about how these climate models work. They're pretty cool.
Oh, that sounds great. All right, you are listening to Linear Digressions.
I think these climate models might be fairly familiar to a lot of people at this point because, they get a lot of popular coverage. The idea, though, is that there's these scientists and they study the way that the climate works on Earth, and we're trying to project out into the future what the climate is going to be like, let's say, in the next 100 years or so. And what you usually hear coming out of these studies is that there's sort of a range of expected temperatures that are associated with various levels, especially if we're assuming that there's sort of anthropogenic, like greenhouse gas effects and things like that, and then effects that come as a result of those potentially. That under various scenarios, what's the amount of like global warming and climate change we can expect over the next N years. So the question is like, what do those models do, and where do these numbers come from?
So the models aren't saying 5 years from now it's going to be this hot in June.
No, these are things like what's the overall trend, usually on the scale of like decades or so.
Got it, okay.
And as you can imagine, these are pretty complicated models. And they're complicated. The first part of why they're complicated is because there's several different types of systems that you would want to simulate for one of these models, and then all the systems will interact with each other. So there's three big sort of subsystems that you might want to simulate. One is the atmosphere. So what's going on in the atmosphere in terms of things like wind, pressure, what's the composition of the atmosphere, and if you have the sun radiating on the Earth with a certain intensity, then how does the atmosphere sort of absorb or re-emit that radiation when it re-emits it?
So like one of those things that you may have heard of is greenhouse gases, right? So carbon dioxide and methane and whatnot. But of course there's a lot more that's involved with atmospheric simulation. Right.
So some of the things that are always going to be happening in the atmosphere are things like clouds, and there's going to be chemistry that's going on in the atmosphere, and there's going to be sort of inherent heat capacities of the molecules in the atmosphere. And then to that you can add contributions of various kinds of gases, say from anthropogenic sources or from things like deforestation. Volcanoes, as it turns out, can have a really big effect, short-term effect, but significant on the atmosphere, and they can cool the Earth measurably. So you have the atmosphere, and then of course all of these sort of complicated things that can be happening are also being mixed around by the fact that the Earth is spinning. So it's not just this static kind of ball of air that can be radiating and relaxing and what have you, but it's all getting like churned in together.
Yeah, and if you want to get an idea of what those how complex those interactions could be, you can look at Doppler radar stuff, or if you want a more specific and visible example, you can look at the surface of Jupiter at any given time. It's very swirly.
Oh, yeah, for sure. Then interacting with the atmosphere, you usually have the land, which is usually land is a little bit simpler to simulate from what I can tell. And I'm no expert here, but the idea is that land doesn't, I think, churn around and move the way that atmosphere does. But this is where you take into account things like the vegetation on the Earth. Potentially, if you have something like there's land that has carbon that's been frozen in it in like permafrost, let's say like up in the Arctic Circle, and then the permafrost starts to melt, then there can be like carbon that can enter the atmosphere via the land, things like that.
Also, I want to take this opportunity to say one of my favorite words, which is albedo, which is the reflectivity of the Earth. Or of
the
something.
Albedo is very important, as it turns out.
That's true.
Albedo also related to clouds, and as it turns out, as I was reading up on this, it's super hard for us to simulate clouds. Like, clouds don't work particularly well in these models, as it turns out.
Uh-huh.
But that's neither here nor there. So now we have the atmosphere, we have the land, and then the third big thing that you might couple in is, you want to take a guess?
The Earth's core. No, I'm going to guess the ocean.
Yeah, it's the ocean. So this includes things like, obviously, ocean currents, the surface temperature of the ocean, and then usually sea levels and the icebergs and stuff like that as well.
Right.
And so you have sort of all of these complicated systems, and each one of them, you could imagine, would be its own very complicated system in its own right to simulate. But of course, they're all interacting with each other.
Yeah,
So,
I was kind of going to say that. Like taking these three systems and separating them like this feels a little bit artificial, because really the lines between these systems are not necessarily so clear cut, right?
yeah, so the way that they do these simulations, and that helps with sort of the information passing between the different subsystems, is they take the entire Earth and they split it up into cells. And sometimes they split it up sort of latitude, longitude. Sometimes they split it up using, like, basically the exact way that they split it up is one of the things that makes all the different simulations a little bit different. And there are sort of pluses and minuses to all the different schemes that you can imagine of breaking the Earth into cells. But then you assign basically all of the surface area of the Earth. Each, there's sort of like blocks of it, and each block then you simulate sort of independently with the other ones, and then the interfaces between each block and its neighbors is where you have to worry about information that can sort of get passed from one to the other. So if you have one spot of the Earth that's really warm, then you can imagine that heat then can like propagate to the neighbors over a series of time steps, along the interfaces. So now we've kind of split it into the problem of, can we simulate each of these little boxes independently, and then can we share information between them, and then repeat the exercise of them, taking this new information, simulate each of them independently, spread it around, if that makes sense.
That's interesting. In kind of a fuzzy way, reality does this already. I mean, I guess you could argue about what the granularity would be, but you could say like individual atoms or something like that would be your cells. Actually, that's really confusing to use the word cells in that case. But ultimately, it's a bunch of small things interacting with each other. Of course, we can't do a simulation of a bunch of atoms with a bunch of different atoms for so many different reasons. But in a way, this is kind of representing reality in a much more zoomed back and probably much more inaccurate way as well.
So definitely inaccurate. Let me pose a question for you. So
Sure.
We've now said we're going to split the entire surface of the Earth into these little boxes, and you can imagine that just depending on the size of the box that you make, you can very rapidly increase the computational intensity of what you're trying to do. For each one of these boxes, also, you have a number of different measurements or parameters that you would need to worry about. So it's things like the temperature and the air pressure and the composition of the atmosphere, like chemical composition, whatever. We could go on for a while thinking about all the things that might be relevant and how they interact with each other. So depending on the granularity of the grid, you can get very computationally expensive. So the most fine-grained simulations that we're able to do at this point for like the entire Earth, for any kind of like reasonable time frame, what do you think the size of those cells is? Like the finest grain that we can get?
I don't know. My intuition says like maybe 10 by 10 kilometers or something.
The number I heard was 100 kilometers.
Oh, no.
Yeah,
I was
so
an order
it's-
of magnitude off. And an order of magnitude in this case is 2 orders of magnitude-ish.
Well, it's
because
really
it's
3
in-
because we're also going up.
Oh, no.
Yeah.
You're right. We're talking about the atmosphere.
Yeah, but you
Okay,
can...
so I was way off.
Yeah, but you can see how, coarse grained doesn't even, like, really quite begin to get there. Because, obviously,
Right.
you can imagine lots of phenomena that could be happening on a much smaller scale than that. And that we have to kind of aggregate right now for lack of a better technology as it stands at the moment.
Right. I mean, if you look at like Los Angeles or Beijing or something like that, those could have a pretty large impact as opposed to, some uninhabited cube in Siberia.
Yeah, the other thing that can be complicated about the way that you split up the problem for yourself is it's not just divided in space, but they also have, they're splitting it in time. So we have the idea of we're going to run a little simulation, exchange information between all the cells, run another little time step, exchange information. And so the granularity on which you do that time stepping can also have a big impact on, well, I don't know how big of an impact it has on like the final numbers that you get out, but obviously you can make choices that make it more or less computationally intense, but then maybe with bigger error bars or something like that.
Yeah, that makes sense.
And so what they do with these climate models is you can see now how there might be many different ways that you could model some of the details of the atmosphere or the details of the land. And of course, there are different assumptions that we can introduce about things like the rates at which certain types of gases are being introduced into the atmosphere or whatever. And so there's also a number of different ways that you can actually do the gridding and the time stepping, the exact geometry that you use and how fine-grained it is and things like that. And so then you can see how you get a range of answers out at the end of this. You might have a number of different climate models and you're running all of them instead of having just one and you say, like, this is the climate model, because we usually don't have enough confidence in any one piece of that that we would never consider that something else could be a little bit better. So you kind of ensemble them, so to speak. You run it many times. Each time you might get slightly different answers, and then you run several different versions of the model, and then you start to average over the entire set of all the models that you've built, and that gives you some of those ranges.
Got it. Okay, Katie, I do have a question, though.
Yeah.
Which is, like, we've got all these models and everything. How do we know that these are actually predictive of reality, right? I mean, like, we're extrapolating into the future, but how do we know that they actually, are representative of reality?
Right, really good question. And the answer is we have it try to predict the past. So we already have information about what was happening 10 or 20 or 50 years ago. And we have pretty good data is what I mean that we've collected.
Got it. Because we've been recording this stuff for a really long time. We just haven't necessarily been doing crazy analyses like this.
Yeah, so you just start up your model before let's say you start up your model N number of years ago, you have it run for a while, and then you see if after an appropriate number of CPU cycles where it's making a prediction for what the weather was like in 1980, if that's, roughly around what the climate seemed to be like in 1980. Maybe not specifically like 1980, but if it's getting like the general trend.
Okay, so like as an example, started in 1900, give it all of the input parameters and, set up your model and then have it run and then see how it's doing in 1950 and compare it to the actual 1950s weather or 1960 or 1970 or 1980 or present day. Yeah,
that's right. Although one of the things that I thought was really interesting, I was learning about this, there's this really great blog called Climate Site, like climate and then SIGHT, that looks like
Site.
That it was just run by a PhD student in climate science, and so she knows tons about this. And what she was saying on this blog post, and we'll post a link to it in the show notes, what she was saying is that one of the things that they do that sometimes even works better than trying to start it 100 years ago is you just start it at the beginning of the Earth. Like you start with a...
What?
So you start with the Earth, and you have the continents and the composition of the atmosphere, and that's kind of it. And then you turn on the sun. And then you start.
Wait, and then you turn on the sun?
Well, yeah. You say there's radiation and it's coming in at like a certain rate.
Oh, that's cool.
And then you start spinning it around, and you let it go for a while until it's kind of in equilibrium.
My hope is that you wouldn't start spinning it around, but start it already spinning, because that's...
Well, I don't think they simulate at the level of like the individual people and how weird that would be if you were on a cold, dark planet.
That's not what I was thinking. But...
I'm just teasing you.
Yeah.
And so you kind of start it from year zero, and that sometimes that can be an easier starting place in some ways than trying to sort of join in midstream and kind of pick it up after it's been going for several million years.
So how well do we actually understand? I mean, we're making these models, right? And we've talked about a lot of data sciencey and machine learning stuff, like neural nets are a good example of something that we can build, or we can build through some more indirect process. And we end up with this model, and we don't really know how the heck it works, but somehow it works. Like, is this one of those, or are we actually like feeding in things and we kind of understand how we've built it?
So little column A, little column B. There are places where these models still surprise us in the sense that we get, as we're measuring things, especially as climate change is happening and there are changes that are taking place in the Earth, and hopefully these models would be able to give us some predictions about what magnitude those changes might take. There are still places where the Earth surprises us, usually lately not in reassuring ways. So one thing I'm thinking of is there's a set of models and they give us an estimate of the Arctic ice cover over the coming years. And as it happens, we're pretty far outside of that band of models right now. It looks like the ice is disappearing much more quickly than most of these models seem to be predicting. So
the bad end of that.
Yeah. So, which is sort of understandable. You're trying to use these models to predict something that's pretty unprecedented, I think, in the history of the sorts of things that we've been had to think about modeling in the past. And so, whenever you're going through like a sharp transition like that, you shouldn't necessarily expect to get it quite right. It can be really hard to get things when they're changing really quickly. Equilibrium is much nicer.
Yeah.
That having been said, there's some things that I was learning about these as I was reading about them that I thought were really cool. One is that, and the one that we'll end on, is that El Nino, as it turns out, is not something that climatologists, it sounds like, have a super firm theoretical grasp on it.
Yeah, that's every some number of years we get a bunch more rain, right?
Well, yes. I mean, I would say it's a little bit deeper than that. It's that there's this...
I'm just thinking from California's perspective.
Californians. So it's...
the whole world revolves around us, I think.
Right. So the thing that gives you your rain is the fact that there's these sometimes warmer than usual and sometimes colder than usual patches of water out in the Pacific Ocean. So if it's warmer, that's El Nino, and then La Nina is where it's colder, I think. So
okay.
You can get it both ways, but I think El Nino has a bigger climatological effect, and when that happens, like you said, you get more rain on the West Coast, and sometimes that has effects that sort of propagate to other corners of the globe. Like I think I was hearing that because there was a strong El Nino this year, that might have some interaction with other atmospheric effects, and we had kind of a mild winter in Chicago, and maybe El Nino had a little bit of something to do with that. Anyway, the point is, El Nino is this huge atmospheric effect that we don't totally understand why it happens.
So how do we put that into our models?
We don't. The thing that's cool is that a lot of these models will just have El Ninos sort of arise organically.
Wait, what?
So even though we don't understand, it's so clearly El Nino is this emergent effect, right? You have this really complex system. Who knows what's going on, but then you get sort of these macroscopic effects because of these complex interactions. We don't understand the exact mechanisms by which these microscopic interactions give rise to like the bigger things like El Nino, but we've got maybe the microscopics of the climate simulations good enough that we're able to get the macroscopic effects out. So we don't put El Nino in. It's that El Nino kind of comes out on its own given the baseline assumptions that we've built into our model, which I think is really cool.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.